Dr. R. Hemavati is an assistant professor in mathematics in Queen Mary's, Chennai. She has specialized on functional analysis. Having 12 years of experience in teaching, she has won various awards for her performance. She has published papers in 14 international journals, 3 national journals, and has presented papers in 10 international and in 5 national conferences. She is also one of the editors for an international journal.
Welcome to UGC lecture series. The subject is Statistical Methods 1. So far we have dealt with random variables, discrete and continuous, and its respective probability functions, probability mass function and probability density function, and the cumulative distribution function CDF for both the types of random variables. In this session, we are going to deal with the mathematical expectation of a random variable. After dealing with random variables, respective probability functions, cumulative distribution function, the next in series is mathematical expectation of a random variable. We will study the concept of mathematical expectation of random variable in both the cases, discrete and continuous type. So, the definition of expectation of random variable goes like, if x is a discrete random variable, then expected value of x denoted by E of x, E stands for the expectation itself, is defined as E of x is equal to summation x into P of x. Here the summation will range for various values of x. Even if you want, you can write x as xj and into P of xj, so that j ranges from 1 to n, taking variety of values of x. Provided the series is absolutely convergent. What is meant by absolutely convergent? Absolutely convergent means E of modulus of x. So, E of modulus of x is equal to summation modulus of x into P of x, which is equal to summation modulus of x into P of x. Is convergent means we write it as less than infinity. So, that is what we call the series is absolutely convergent. Similarly, if x is a continuous random variable, the expected value of x is denoted in terms of integration. For discrete case, we have to use summation. For continuous, we have to use integration. Integral x into f of x dx. And the limits may vary from minus infinity to plus infinity. Here also the integral is absolutely convergent. So, here also you should have P of E of modulus of x is less than infinity. So, based on the expectation of x, we have some measures which can be calculated, that is mean of x. Mean of x can be calculated through expectation as well as through moments, which you are going to study in the next further sessions. So, mean of x is equal to expectation of x. So, mean of x can be described for both the cases, sigma x into P of x if x is discrete and integral x into f of x dx if x is continuous random variable. Okay. Similarly, we define variance of x. Variance of x is also a measure where we can calculate variance of x through the expectation as variance of x, shortly written as VAR of x, is equal to expectation of x square minus expectation of x the whole square, where E of x is already defined in the previous slide, and now we define E of x square. E of x square is summation x square into P of x, whatever the function which comes under the within the brackets of expectation will come along with the P of x in its summation or integration. This is for x is discrete, and for continuous its integral x square into f of x dx if x is continuous. Okay. So, after finding E of x square, you substitute here, and e of x which was told in the previous slide, you find out and substitute here, square it, subtraction of these two gives you variance of x. Now the properties of expectation. Properties of expectation. We will see one by one the various properties of expectation to understand the mathematical expectation further. Property 1 says if c is a constant, then expectation of a constant is constant itself. That is, it is degenerate. Expectation does not make any difference with the constant. Let us see how this is achieved. Let me take the random variable x as a continuous case so that we achieve e of c is equal to c. When we prove it for continuous random variable, in the similar way we can prove it for discrete random variable also. So first we will prove it for continuous random variable, which is similar for discrete random variable also. Okay. So the proof goes like, take the left hand side e of c, according to the definition integral minus infinity to infinity c into f of x dx. This is what is expectation definition. E of x is integral x into f of x dx. So e of c is, in the place of x you are having c into f of x dx is equal to c is a constant, it can be taken outside. So minus infinity to plus infinity f of x dx. And this particular integration stands for total probability is equal to c into 1 is equal to c. Hence proved. The next property is, if c is a constant and y is equal to h of x is a random variable, then that is here y is equal to h of x means this is a function of a random variable which is also another random variable, we call it as y. Then e of c into h of x, when the constant is getting multiplied with the random variable, the constant comes outside the expectation. And if the constant is getting added with the random variable, the constant as such, when you distribute expectation inside, e of h of x plus e of c is again c. Let us see how the proof is achieved. First, to prove e of c into h of x is equal to c into e of h of x. Okay. Take the left hand side, and again we are going to prove it for a continuous random variable. So left hand side is e of c into h of x. According to the definition of expectation in terms of continuous random variable, it is c h of x into f of x dx. Okay. C is a constant, I will take it outside the integration, minus infinity to infinity h of x into f of x dx. Whatever be the random variable or whatever be the function which accompanies along with the PDF of x is called the expectation of the particular random variable. So again by the definition it goes c into expectation of h of x. Again this is achieved by the definition of expectation of a random variable, which is equal to your right hand side, hence proved. Next we have to prove e of h of x plus c is equal to e of h of x plus c. So again take the left hand side is e of h of x plus c. We will prove this theorem again for continuous random variable. So from minus infinity to plus infinity, as already told by the expectation definition, whatever is there along with the expectation will come inside. So h of x plus c into f of x dx. So this is, I will split this as two integrals, minus infinity to infinity h of x into f of x dx plus integral minus infinity to infinity c into f of x dx. So along with the f of x, h of x is there. So this stands for the definition expectation of h of x, and when the c comes outside, like the arrow mark coming outside, c into the remaining integral is minus infinity to infinity f of x dx, which is equal to 1. which is your right hand side, hence proved. So, third property is linearity property of mathematical expectation. So far we have dealt only with one random variable and the function of random variable. This property particularly says when you take n random variables at a time, if x1, x2, x3 etc. up to xn are n random variables along with its constants a1, a2, a3 etc. up to an or any n constants, then expectation of summation sum of n terms is equal to summation of their respective summations of their expectations. How to prove this? Take the left hand side is expectation of summation of ai into xi, where I is given to be from 1 to n, although it is not specified, as I taking the value from 1 to n, there are n random variables. So according to the definition of random variable, this is integration minus infinity to infinity summation ai xi, I is equal to 1 to n into f of x dx. Okay. So this is from minus infinity to plus infinity a1 x1 plus a2 x2 plus etc. plus an xn into f of x dx. This one particular integral where the integral inside integrand is summation of n terms. So this can be written as summation of n integrals. Okay. So minus infinity to infinity a1 x1 into f of x dx plus minus infinity to infinity a2 x2 into f of x dx plus etc. The last one is minus infinity to infinity an xn f of x dx. Okay. So this is equal to a1 into integral x1 f of x1 dx f of x dx from minus infinity to infinity plus a2 minus infinity to infinity x2 into f of x dx plus etc. plus an integral minus infinity to infinity xn f of x dx. But accordingly the integration stands for e of x1. So a1 into e of x1 plus a2 into e of x2 plus etc. an into e of xn. This is nothing but summation I is equal to 1 to n ai into expectation of xi, which is your right hand side, hence proved. We shall have a break. Welcome after the break. Before the break we have seen the definition of mathematical expectation of a random variable for discrete and continuous case, and we are also seeing some of the properties of expectation. We have so far seen 3 properties. Now we will deal with the fourth property. The fourth property says e of ax plus b is equal to a into e of x plus b. Okay. So the proof is take the left hand side again, e of ax plus b. We are proving this for continuous case. As proved for continuous case, you can prove it for discrete case also. This is equal to integral minus infinity to infinity ax plus b into f of x dx. Writing this as 2 summations and accordingly separating the constants, this can be written as a into integral minus infinity to infinity x f of x dx plus b into integral minus infinity to infinity f of x dx. This particular integral stands for expectation equal to a into expectation of x, and the second integration stands for the total probability, which is equal to 1. So b into 1, which is your right hand side, hence proved. Okay. So what is the next property? Next property says if x is greater than or equal to 0, then the corresponding mathematical expectation is also greater than or equal to 0. So how to prove this? We take expectation of x, according to the definition it is minus infinity to infinity x into f of x dx. Here particularly x is given to be greater than or equal to 0, therefore the whole integration is greater than or equal to 0. Because f of x is already defined to be a PDF, according to the PDF probability density function, f of x is non-negative. So, x is non-negative given as x greater than or equal to 0. At the same time already known f of x is non-negative according to the definition. Therefore, the whole integration is an integration of a positive quantity. When limits being substituted, we will also always have greater than or equal to 0. So, therefore, when x is greater than or equal to 0 implies E of x is also greater than or equal to 0. Okay. So, the next property is if x and y are two random variables such that the relation between x and y is represented as x is greater than or equal to y, then E of x is greater than or equal to E of y. Okay. How to prove this? We have x is greater than or equal to y, mentioning that x minus y is greater than or equal to 0. Okay. So, x minus y, if you take some other random variable z, we have z is greater than or equal to 0. So, when z is greater than or equal to 0, by the previous property, that is property 5, we have p expectation of z is also greater than or equal to 0. So, this implies E of x minus y is greater than or equal to 0, because z you are taking as x minus y. So, E of x by linearity property or addition property, E of x minus E of y is greater than or equal to 0. So, that is E of x is greater than or equal to E of y, hence proved. What is the next property? Modulus of E of x is less than or equal to E of modulus of x provided the expectations exist. Obviously, when expectation of x was defined, we told the series should be absolutely convergent. So, modulus of expectation of x will exist, and at the same time expectation of modulus of x also will exist. We have to prove the inequality alone. Expectation of modulus of x absolute is less than or equal to expectation of its absolute value. Okay. So, how to prove this? Take E of x and its modulus. This is according to the definition integral modulus of integral minus infinity to infinity x into f of x dx. When you take the absoluteness inside the integration, this becomes less than or equal to integral minus infinity to infinity modulus of x into f of x dx. The modulus being distributed only for the integrand x into f of x. But already we know f of x is non-negative. Modulus absolute value means there is any negative value that will become positive. But already f of x is non-negative as per the definition of PDF. Therefore, this is equal to integral minus infinity to infinity modulus of x into f of x dx. But what does this particular integral stands for? F of x is accompanied with the modulus of x. Therefore, according to the definition of expectation, this is expectation of modulus of x. So, starting from modulus of expectation of x, we have ultimately got expectation of modulus of x. In between there is a lesser than or equal to symbol. Therefore, this particular thing implies modulus of expectation of x is less than or equal to expectation of modulus of x. Hence, proved. Based on the expectations definition we have seen and the properties we have seen, these particular questions can be arised. Define mathematical expectation of discrete random variable and define mathematical expectation of continuous random variable separately, and state and prove any 3 properties. So far we have seen some 6 properties, 3 properties can be asked or 4 properties, this number may vary, and state and prove the linearity property of mathematical expectation. In mathematical expectation further there are more properties, but according to the continuity of the sessions, we are yet to study the bivariate probabilities where x and y both will be dealt. X is discrete, y is discrete. When both are dealt, accordingly we have 2 more properties of expectation, that is addition theorem of expectation and multiplication theorem of expectation, which will be proved later when you study the bivariate random variables. So now we are studying univariate random variables. For univariate random variables studied so far, these are the properties of mathematical expectation we are dealt. Okay. Some illustrations in mathematical expectation of a random variable can be seen so that you understand the concept of mathematical expectation very clearly and further. Okay. So the first illustration goes as two unbiased dice are thrown. Find the expected values of the sum of numbers of points on them. So we will prove this, we will find out the expectation of sum of numbers. When two dice are thrown, as already discussed, the sample space goes as 1, 1, 1, 2, etc. up to 1, 6, varying from 6, 1 to 6, 2, etc. up to 6, 6. So this is one point on first die and this is another point on second die. So there are totally 36 possibilities. This type of problem we already seen in dealing with the probability mass function. So now for this particular random variable, how to find out the expectation? Okay, x is defined to be sum of points. Sum of points. So starting from 1, 1, you are ending with 6, 6. So starting point is 1, 1. The sum of points is 1 plus 1. So starting from 2, we have 3, 4, etc. It goes on up to it ends up with 6, 6. The addition of 6, 6, sum of points of 6, 6, which is the last possibility, it gives you 12. So x is taking the value from 2, 3, 4, etc. up to 12. All are natural numbers. There is no interval. X takes particular values 2, then 3, then 4, then 5, etc. It goes on up to 12. What are the corresponding probabilities for that? Okay, we will form the tabular column. This type of already we have seen, so I go little faster. This is x and this is p of x. For 2 it is 1 by 36, for 3 it is 2 by 36. Similarly, it goes on up to 12. It goes on up to 12 and 12 it again ends up with 1 by 36. Okay, 2 is achieved with 1 by 1, 1, so 1 by 36. What is x into p of x? Multiply x and p of x. 2 into 1 by 36 is 2 by 36. X into p of 3 into 2 by 36 is 6 by 36. Likewise, last you have 12 by 36. So the summation, when you add, it is summation x into p of x. That is your expectation of x equal to, adding all the x into p of x, it gives 252 by 36, which is equal to 7. So E of x equal to 7. That is expectation of the sum of points on the two dice is 7. What is the next illustration is, find the mathematical expectation of the number of tosses of a coin which is tossed until a head appears. A coin is tossed until the head appears. This particular type of problem for finding the probability of the number of tosses of a coin which is tossed until a head appears is called Huggins problem. For this Huggins problem, you are finding the mathematical expectation. Okay, how to find out the mathematical expectation for the number of tosses? X, you take x as number of tosses required to get first head. You are throwing the coin for the first time and the head appears means the game ends. So that is one possibility. Another possibility is you are tossing the coin and tail appears. So you have one more chance, you have more chances to toss the coin because the coin is tossed till the head appears. So the first time you are tossing, the tail appears. So second time you are tossing, if the head appears, there ends the game. Otherwise, another possibility, first time tail, second time tail, third time head. Another possibility T, 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 H. It likewise it goes up to infinity. So, what is the number of tosses for this? If you see, this is possibility, and the number of tosses is H, only one time it is tossed, so 1. Tail and head, so 2 times the coin is tossed, so this is 2. Here 3 times tossed, 4 times tossed, etc. up to infinity. So, this is your x values. What about P of x? What is its corresponding probability? For appearance of head it is 1 by 2. For appearance of tail and head it is 1 by 2 into 1 by 2. For appearance of tail, head it is 1 by 2 into 1 by 2 into 1 by 2. This is 1 by 2 whole square, this is 1 by 2 whole cube, likewise it goes on up to infinity. So, after this, after x, after P of x, x is 1, 2, 3, etc. up to infinity, and your P of x is 1 by 2, 1 by 2 square, 1 by 2 cube, etc. up to infinity. So, x into P of x is 1 by 2, 2 into 1 by 2 square, 3 into 1 by 2 cube, etc. up to infinity. When you add, that is your expectation, E of x is equal to sigma x into P of x. We will add the infinite series 1 by 2 plus 2 into 1 by 2 whole square plus 3 into 1 by 2 whole cube plus etc. it goes on up to infinity. 1 by 2 is constant, we can take it outside, which is common, taken outside. 1 plus 2 into 1 by 2 plus 3 into 1 by 2 square plus etc. up to infinity. This is compared with an infinite series like 1 plus 2x plus 3x square plus etc. up to infinity, where x is equal to 1 by 2. And this particular infinite series has the formula 1 minus x whole power minus 2, where x is substituted as 1 by 2. So, 1 by 2, 1 minus 1 by 2 whole power minus 2, 1 by 2, 1 by 2 whole power minus 2 equal to 1 by 2 whole power minus 1, which is equal to 2. So, the expectation of number of tosses until a head appears is 2. Summary of this session is, after studying the concepts of random variables along with its probability function, we take the next step by studying mathematical expectation of a random variable both in continuous and discrete case. So, after defining expectation, we are studying some properties of expectation, and to understand further the mathematical expectation of random variable, we will be we are working out some problems on mathematical expectation of a continuous random variable. In this session, we have seen some 2 illustrations of finding mathematical expectation of a random variable which is discrete. Thank you.